All right, we're going to start. I'm going to set up a little bit of chapter 10 here. This will be the last topic we'll cover. Not lecture. Moments of inertia. Congratulations, you've arrived at the last topic I would normally cover in a statics class. Moments of inertia. What is that? And again, that's chapter 10 in the Hibbler text. I don't know what text, if you're not in my class and you're joining us from somewhere in the interwebs, welcome. I don't know what chapter you're in. But we're going to talk about moments of inertia here. Right? Moment of inertia in the x direction, or about the x-axis, if I'm talking in two dimensions, it's going to be the integral across the area of y squared with respect to area. And the moment of inertia about the y-axis is going to be this integral across the area of x squared with respect to area. Steve, what the heck is that? What does that even mean? Well, this is what the moment of inertia represents. It represents inertia. It represents a measure of an object's inertia or resistance to rotation. That's kind of the simplest way to think about it. Now, there's different kinds of moments of inertia that we could measure, but this one, just to keep it simple, because without context, you're really not going to understand, in my opinion, you probably won't understand too much about what are the different kinds of moments of inertia. This moment of inertia we're going to talk about here, just understand or think about it this way to keep it simple. It represents the resistance of an object to inertia, to rotation. It's similar to mass for rotation. It's not a perfect analogy, but it gets pretty close. It's not bad. So think about where the sum of forces is equal to ma, and normally in statics, A equals 0. But your sum of force vectors is going to represent the sum of, or is going to equal the mass times the total acceleration applied to an object or a body. And again, in the statics class, we're dealing with equilibrium where things are not accelerating. They're not changing with respect to time. Now, sum of moments will be measured by the moment of inertia, the resistance to rotation, multiplied by the angular acceleration. Again, in statics, we're assuming that nothing's changing with respect to time, nothing's accelerating. So in statics, the angular rotation is not accelerating. The alpha value is not accelerating. But this is what the moment of inertia roughly represents, is this quantity, this resistance to rotation. And we could talk about what's its resistance to rotation about an x-axis, what's its resistance to rotation about the y-axis. That's essentially what these are representing, is trying to describe this moment of inertia. Now, why would we care? Well, one, in a dynamics class, or in kind of advanced or applied physics class where an object is now beginning to rotate, we would not need to be able to track at what rate is it rotating, at what rate is its rotation increasing. Well, if I could determine the total moment or the total torque applied to an object and its moment of inertia, I could figure the rate at which its rotation is increasing. Same thing I could do with its translation, sliding or moving force, or moving acceleration is going to be based on the net force. The other thing, so that's in kind of a dynamics or study of motion type of class. Also, in strength of materials, there's often sigma, which is the stress. It's a type of stress involved inside of a solid object. Materials can only handle a certain amount of stress, and that stress is going to be proportional to the bending moment. Remember the internal bending moment that we found in Chapter 7? We plotted diagrams for that. That doesn't go away, by the way. So in a strength of materials or mechanics of materials course, that stress is proportional to that bending moment. It's also proportional to essentially the thickness of the beam or the structure. This is what we call the distance from the neutral axis. That will make more sense later. Divided by the moment of inertia of that shape. My over I is sigma. And the stress determines whether something's going to break or not, depending on, certain materials can only handle a certain amount of stress. How do we find that stress? Well, I need to know this moment of inertia that we're introducing conceptually here. The calculus, again, if you're allergic to calculus, you may not be in the right place. But, with that said, I'm going to approach this kind of like we did with centroids from a double integral approach. Let's see if we can do a real simple example first. Okay. Example. Let's just keep a very simple triangular region. We'll say on the y-axis it goes up to h, and on the x-axis it goes out to b. So base and height on the x and y. So let's say we want to find the moment of inertia about the x-axis for this particular shape. Okay, well, remember the moment of inertia is going to equal the integral of y squared with respect to area. Now, if you look in your textbook where they are assuming you may or may not have had multivariable calculus, they will take this approach. You're welcome to pause this when I show it. Basically, I need to be able to describe this dA in a single variable. Well, how do I describe that dA in a single variable? Well, I need to look at a differential area of this thing, some differential height y. Now, this is a triangle, a height b and a distance, base, a height h at base b. So this expression, it's a linear expression along here. Y is equal to mx plus b. Well, b plus b is 0. It's your y-intercept is 0. Your rise is h. Your run is b. So this is your slope, h over b. Y is equal to h over bx. That's the equation for this line. Okay. So if we pick some arbitrary location x to describe this differential slice of area here with thickness dy, I need to describe the size of this differential area. Well, it has a thickness dy, that's this. Its width is this quantity. How do we know this quantity? Well, again, I'm not going to ask you to do these. If you can do these by double integral, that's how I would approach this. So its thickness is dy. Again, I'm trying to find this differential area. Well, its thickness is dy. Its width is this amount. How do I know that? Well, this location at some arbitrary x, again, the equation is y is equal to h over bx. That's at some arbitrary value x. Or the x value itself, I solve this expression for x. X is by over h. So that means this distance to here, to get out to an arbitrary x, I've gone by over h distance to get there. And the entire distance is b, so the remainder out here, the width of dA is b minus this quantity by over h. The product of this and this is the width, this is the height, that gives me the differential area. So if I take Ix is equal to the integral of y squared with respect to area, then I can substitute this in for the differential area. This is the integral of y squared b, quantity b minus by over h with respect to y. And then this is a single variable calculus problem we can solve. B and h are constants. And you can see the solution. That works. Feel free to pause it, take notes. You want to compare it. If you're like, Steve, I am not doing that. Show me the double integrals. I got you. Let's do that. You may have already seen my double integral notes up here. I'm going to approach this with double integrals. So if I want to approach this as a double integral, I'm integrating across this area, so I need to integrate it across x and y, kind of like I did with centroids. So I'm going to do two integrals. I'm going to integrate y squared. I'm going to go first with respect to y, just like I did with centroids, and then I'm going to go with respect to x. So dy dx is going to give me dA. Excuse me. Now I need to find limits for these integrals. Again, this expression, as we said a second ago, your rise over run is h over b. It's a linear equation, and it intersects the y-axis at 0. So mx plus the y-intercept, that's going to be h over b x. So I'm going to go from 0 on the y-axis. I'm going to go from 0 up to this function. So I'm going to go from 0 up to h over b x. On the x-axis, I'm going to go from here all the way out to b. So I'm going to go from 0 all the way out to this b value. And then I just go ahead and compute these. So I'm integrating y squared with respect to y. So I'm going to leave the outside integral alone, integral from 0 to b. We're going to evaluate the inside integral. I'm integrating y squared with respect to y, so I'm going to end up with y cubed over 3. And I'm going to integrate that, or I'm going to perform that along the interval from 0 to h over b times x. And then I need to integrate the result of that with respect to x. Ix. I'm going to plug these in, so when I evaluate it at 0, I'm going to get a 0 for the negative term, so I'm just going to worry about the positive term. So I'm going to integrate from 0 to b. I'm going to plug this in here, so I'm going to have h cubed over b cubed. So I'm going to pull out the b and the 3 in the denominator, so it's over 3. I'm going to cube the b, so h cubed over 3b cubed, and I'm going to cube the x, so times x cubed dx. So now I need to integrate this function with respect to x. This is all constant, so I'm just going to pull it out of the integral. Then I'm just integrating x to the third with respect to x. So I've got h cubed over 3b cubed. That's all my constants. Pull those out. Integrating now the x to the third. That is x to the fourth over 4, and that's going to be evaluated from 0 to b. So you see what I've got here. You can skip as many of these steps as you're comfortable with. I'm going to leave this h cubed 3b cubed over 3b cubed alone. I'm going to go ahead and plug in b here. That's going to be, again, you could probably skip this step. That's b to the fourth over 4. I've got b to the fourth in the numerator. I've got b to the third in the denominator. I've got 3 times 4 in the denominator. So this is going to be, I'm going to write it bh cubed, or you could write h cubed b, and it's going to be over 12. This is my answer, which if you do it the way they would do it in the book, assuming that you don't know how to do double integrals, and finding this dy as a function of, dA as a function of dy, you'll get the same result, bh cubed over 12, which is what we got. Double integrals, calculus. It's kind of cool. It works. Okay. Now that's if I've got a function and I need to know about this bottom x-axis. Now I showed you guys last time in the back of your book, any good statics book, ours is no different. Ours is a very good statics book. In the back of your book, you should have these different shapes. This is the inside back cover. Now I can't get everything in there, but notice for a triangle, Ix, it's saying Ix is 36 over 1 over 36 bh cubed, which is not what we got, but notice they're saying that's about the centroid axis. They're calling this the x-axis. The x-axis passing through the centroid, 1/3 of the height above. So it's actually different because we calculated the rotation about this x-axis. At the bottom of the shape, inside your textbook, it's going to give you the moment of inertia about the axis passing through the centroid, which for us would be like right here. So they're saying the moment of inertia passing through this axis is different than the moment of inertia passing through that. And that would make sense. If you were to take a string and glue this triangle to that string and try to spin it around that string, I would get a different moment of inertia. I would get a different amount of resistance trying to spin that thing. I should 3D print one and bring and just show you. As opposed to if I put a string right through the center of this thing and try to rotate about that center point, it's going to rotate differently and be a little harder actually to rotate about this bottom axis than it would be about the center axis. So about the bottom axis, I've got bh cubed over 12, dividing by a smaller number, so I get a larger moment of inertia. Whereas to the centroid, it's bh cubed over 36, dividing by a smaller number, or dividing by a larger number, you get a smaller resistance to rotation. So there's something going on there. I get a different moment of inertia depending on where the axis is. So how do I rectify that? What do I do with that? Well, there is a concept that we call lecture 19, page 2. It's a nice stopping place. I'm going to stop us here, and we'll start talking about parallel axis theorem on the next video.